Okay, so today we're going to talk about an application of the quadratic function or an application of quadratic functions. And with function notation, what the information that you're being given is you're being told on the left-hand side here that the independent variable is x. So this is the independent variable or the input. Um, That means that when we look at the expression on the right, this is a quadratic expression. The only variable on the right-hand side is x. So you see it's a quadratic expression because x, the independent variable, is being raised to the square, is being raised to the second power. You have a linear term in x and a constant, but the fact that the degree of this polynomial is second degree, and x is the independent variable, and x is the thing that's being raised to the second degree, makes this a quadratic function. This would be the name of my quadratic function. This function is called f. So if I wanted to make a call to this function, the name would be f, and then I just replace the independent variable with whatever number I wanted to plug in for all the x's over here. A, b, and c are numbers. So one thing that this is used for in physics is for the height of a object, a projectile actually that is projected and then starts to free fall. So in this case, the independent variable, the thing that is the input that you have to tell this expression, that you have to plug into the expression, is time. So t, in this case, the independent variable is time, and s, s is the height above the ground. They call it the position. Position is really how far from the ground the object is at a certain time. So if you give this function a time, you plug in a time into the function, and you do all these calculations, the number you get back, s, is going to be how high the object is or how far the object is from the ground. There are a few other things here other than t and s. For instance, g. G is a constant that has to do with the acceleration of an object due to gravity. So g is the acceleration due to gravity of an object near to the Earth's surface, or at sea level actually. So this is acceleration due to gravity. And we're going to have a few values for that, depending on whether we're dealing with the metric system or the English system. We're going to be dealing in feet and seconds. So this number is going to actually turn out to be 32 when we're dealing with feet and seconds. It's another number if you're dealing with meters and seconds. V sub zero, V sub zero is the initial velocity of the object. Velocity is related to speed, and v sub zero is just the velocity of the object at time zero, how fast the object is traveling at the time that we start to count from, time zero. All right, and let's see. The last thing in here is that s sub zero, and that is just the initial position or the position at time zero. And that should be obvious that if you plug zero in for t, the only term left will be s sub zero, and that's why it's called the initial position. So just by looking at a quadratic expression of time that gives us height, we can know a lot of things. We can know where the object started, what height the object started at, how fast it was going when it started, and we can also know the acceleration of the object due to gravity. That acceleration due to gravity would change depending on your distance from the Earth's surface, or if you were on another planet, it would be a totally different number altogether. For instance, on Jupiter, things accelerate towards the center of that planet faster than they do on Earth. All right. So what we're going to do is we're going to look at this problem. So, an object is observed in free fall. So we have a projectile, and this formula down here is a formula that works for projectiles. All right. So an object is observed in free fall. After 1 second, the object is 224 feet from the ground. After 3 seconds, the object is 192 feet from the ground. And after 4 seconds, the object is 128 feet from the ground. Express the distance the object is from the ground as a function of the time in free fall. So I want to write a function that will give me how high it is from the ground when I plug in the amount of time that it has been falling. All right, well, taking a look back here, remember this is function notation, and with function notation you're being given an ordered pair. For instance, this tells me that x is the independent variable, the first coordinate in the ordered pair, and the f of x, the answer, is y, which would be the second coordinate in the ordered pair. Down here, this tells me that t, the time in seconds, is going to be the first coordinate in my ordered pair, and s, the position or the height above the ground, is going to be the second coordinate in my ordered pair. So I have here actually three ordered pairs, three different ordered pairs, three different times and positions. So I'm putting time in the first uh, time as my first coordinate and height above the ground as my second coordinate. I'm going to come up with three ordered pairs. The first one says after 1 second, so when time is equal to 1 second, this object is 224 feet from the ground. It also says that after 3 seconds, when time is equal to 3 seconds, the object is 192 feet from the ground. And it goes on to say that after 4 seconds, when time is equal to 4 seconds, that the object is 128 feet from the ground. So here I have three ordered pairs, each giving me a time position relationship. The relationship with a certain time and the position above the ground of the object. So what I want to do here is I want to come up with a model. Well, this is not a linear model, and if you check the slopes between consecutive pairs of points, you'll see that you don't have the same slope all the way through. So if all three of these points fit onto the same graph of the same function, it's not a linear function. But we already know that the position function is quadratic. So here's what I'm going to use. I'm going to use this position function. I'm going to plug in those times for t, 1, 3, and 4, and what I'm going to get is what it equals. It's going to equal the position or the height above the ground. So I'm going to get three different equations for each of the different ordered pairs. Let's go ahead and do that. All right. So the first one, actually, let's bring it over so we know what we're doing, so we can see it as we're doing it. This is what we're plugging those ordered pairs into, x and y values, or t and s values in this case. All right, so we're plugging it in here. All right, so let's go ahead and start plugging it in. All right, so the first one, this first ordered pair, since this is a function, this first ordered pair represents the s of 1. So the s of 1, the position at time 1 second, is equal to, it's going to be negative 1 half g times t, which is 1 squared, plus v naught, which is v sub 0, the initial velocity, times t, which is 1, plus s naught, which is s sub 0, the initial position. And when I plug all this in, I should get the height above the ground of 224 feet. So I have that one equation. And then the s of 3, when I plug 3 in, I'll get a different equation here. Is going to be negative 1 half times g times now 3 squared, because I'm plugging in 3 for t, plus v naught times 3 plus s naught. And this is going to equal 192. Because when I plug 3 in for t, I'll get 192 for the height above the ground. 192. And then the last one here is the S of 4. S of 4 is equal to negative 1 half times g. And then for t, we're going to plug in 4. So I get 4 squared plus v naught, v sub 0, times 4 plus S naught. And after 4 seconds, the height of this thing above the ground is 128 feet. So I get these three equations. I have a system actually of three equations with three unknowns. All right? So what I'm going to do first is I'm going to clear the fractions on these first two equations. So the S of 1, I'm going to multiply both sides of this equal sign by 2. When I multiply the left-hand side by 2, and actually I'm not multiplying by 2, I'm multiplying by negative 2 to get rid of this negative 1 half, to clear the fractions. So when I multiply this term by negative 2, I get negative 2 times negative 1 half is 1 times g times 1. So that's going to be just g for the first for the first term in the first equation. Negative 2 times this would just give me g. Negative 2 times this would give me negative 2 v naught, negative 2 v sub 0, and negative 2 times this would give me negative 2 times s sub 0. And this is equal to, when I multiply this by negative 2, I get negative 448. So there's my first equation simplified a little bit. First equation in my system. Let's take a look at the second equation. I'm also going to clear the fractions here by multiplying by negative 2. When I multiply negative 1 half by negative 2, it becomes a 1. And then 3 squared is 9g. So I get 9 times g. And then when I multiply this by negative 2, 3 times negative 2 is negative 6 v naught, v sub 0. And then when I multiply this by negative 2, I still get negative 2 s sub 0. And when I multiply 192 by negative 2, I get negative 384. Negative 384. All right, and lastly, well, this one I don't really have to clear the fractions because 4 to the second power is 16, and 16 divided by 2, or 16 times negative 1 half, is actually just going to be 8, or negative 8. So I get negative 8g, and then everything else just pretty much stays the same, plus 4v sub 0, and then plus S sub 0 is equal to 128. So here I have a system with three equations and three unknowns. And if you take a look, my three equations came from my position function, plugging those ordered pairs into my position function. And the unknowns, my three unknowns are g, the acceleration due to gravity, v naught, or v sub 0, the initial velocity, s naught, s sub 0, the initial position. So once I find those unknowns, I'll be able to answer questions like how fast was the object traveling initially, or how high was the object initially, or what is the acceleration due to gravity in this particular location. And if you look, the question we're actually being asked to do, or the thing that we're actually being asked to find, is or a function that gives us the distance the object is from the ground as a function of time. So we're just being asked for the function here with g, v naught, and s replaced by whatever numbers they actually are. But with that information, we can answer those other questions. So let's go ahead and solve this system of this system of equations. So we're going to solve this system of equations, and the method that I'm going to use is I'm going to use what is called substitution. So this is the method called substitution. What I'm going to do is I'm going to take each one of these and I'm going to give it a letter or a number. Let's call this 1, 2, and 3 for my first, second, and third equation, all right? So what I'm going to do first is I'm going to solve for g in equation 1. So that's my first step. Solve for g in equation 1. And I'm doing that so that I can substitute the value of g into the other equation, and that will actually allow me to get rid of g from two of my equations, leaving only v naught and s naught. All right, so in the first equation, if I solve for g, I get, well, I'm going to add 2v naught and add 2s naught to both sides. So I'll get g is equal to um, 2v naught that I added to both sides plus 2s naught, which I added to both sides, minus 448, which was already there. So this is the value for g. On the right hand side, I have an expression that I can replace all the g's in the other equations with. So let's go ahead and do that. The next step that I'm going to take then from my substitution is I am going to replace or substitute g into equations 2 and 3. So basically, instead of g here, I'm going to write 9 times 2v naught plus 2s naught minus 48. I'm going to replace that g with what g equals. So let's see, we're going to have then, this is going to be 9 multiplied by g, but we just found that g was 2v naught plus 2s naught minus 448, and then that's going to be still minus 6v naught and minus 2s naught, and that's going to equal still negative 384. So there I've plugged my value for g, or my expression for g, into equation 2. Now I'm going to do the same thing with equation 3. So let's see, I'm going to have negative 8 times g, which is 2v naught plus 2s naught minus 448, and then it's going to be plus 4v naught plus s naught equals 128. So I get these two equations now, and if you notice, these two equations only contain the variables v naught and s naught. Take a look. Oops, went too far. These two equations only contain v naught and s naught, v naught and s naught. So I'm going to simplify these two equations now. Well, to simplify the top equation, so I still have these two. To simplify the top equation, I can distribute, and I'm distributing a 9. So I'll get 18v naught, 18v naught, 9 times 2v naught, plus 18s naught, and then minus 9 times 448, which is 4032. And this is then going to be minus 6v naught still, and then minus 2s naught, and this is still equal to negative 384. So all I've done is I've distributed the 9 to all three terms. The top equation is still pretty much the same. And the bottom equation, I'm going to distribute the negative 8. So it's going to be negative 16 v naught minus 16 s naught. And then negative 8 times negative 448 is positive 3,584. So plus 3,584. And then this is going to still be plus 4v naught. 4v, oops, that should be a 4. Plus 4v naught. And then plus s naught equals, and this is still equal to 128. 128. All right, now, next I'm just going to combine the like terms on the left-hand side. So on the left hand side, I have 18 V naught minus 6 V naught, which is 12 V naught. And then I have 18 S naught minus 6 V naught, or sorry, 18 S naught minus 2 S naught, which is a positive 16 S naught. And then this is equal to still negative 384. And then on the bottom, negative 16 V naught, and I have a plus 4 V naught is a negative 12 V naught. And then I have negative 16 S naught plus S naught, which is negative 15, negative 15 S naught. And then here, this is still equal to 128. Oops, I forgot other things here. I combined like terms, but I forgot these numbers here. I have the 18 V naught and the uh, negative 6 V naught is indeed 12 V naught. And I have the 18 S naught and the minus 2 S naught is indeed a 16 S naught. But then I'm actually forgetting about this term. I have to add 4032 to both sides. And when I add 4032 to both sides, I subtract this 384 from it. So the right-hand side will become 4032 minus 384, which is actually 3,648. 3,648. So I combine this term and this term, then I combine this term and this term, and I've moved this term to the other side, making it positive and having negative 348 or 384 subtracted from it, leaving me with this answer. On the bottom, negative 16 V naught and a plus 4 V naught is still negative 12 V naught. A negative 16 S naught and a plus 1 S naught is still negative 15 S naught. But what I forgot to do was this 3,584, I have to subtract it from both sides. And when I subtract it from both sides, it's actually going to be 128 minus this number. And 128 minus this number is actually negative 3,456. Negative 3,456. So I get these two equations that are a lot nicer to look at. They're in standard form here. And what I'm going to do is, since this one is already set up so nicely, instead of continuing with substitution, because I did substitution here, instead of continuing substitution, since I noticed that these two coefficients here are already opposites of each other, I can just go ahead here and do elimination. So for elimination, what I'm going to do is I'm going to add the two equations together. Adding these two equations together will actually eliminate V naught. So let's go ahead and do that. Well, let's see. 12 V naught minus 12 V naught gives me 0. So that cancels out. 16 S naught minus 15 S naught is going to actually give me just S naught. And it's going to equal, and this is going to be 3,648 minus 3,456, which is 192. So I have my initial height. This thing was launched from a height of 192 feet. This is the height or the position at time 0. Now if I want to find the um, velocity, I have both of these equations that I can use that involve the initial velocity and the initial height or the initial position. If I plug the initial position into either one of these, I will get the initial velocity, V naught. So let's go ahead and do that. This is one of my answers though. The initial height or the constant is 192. All right, next I'm going to take the top equation there, 12 V naught plus 16 times S naught. Well, instead of S naught, I know that S naught is 192, and this should equal 3,648. And let's see, 16 times 192 is 3072. I still have my plus 12 V naught and equals 3648. When I subtract the 3072 from both sides, 3072, I'm left with uh, 12 V naught on the left side, and on the right hand side, I'll have 576. And the last step is to divide both sides by 12. Dividing by 12 tells me that V naught is equal to 48. So the initial velocity of this thing was 48 feet per second. And since it's positive, it's 48 feet per second upward, going upward. So this thing was actually not just dropped, it was launched with with an initial velocity of 48 feet per second upward. And let's see. So that's my V naught. And the last thing I want to find is g, the acceleration due to gravity. So it turns out that g is going to equal, well, remember I had this original expression all the way up here for g? So I'm going to use that expression for g. G is equal to 2 times 48 plus 2 times 192 minus 448. And these calculations will give us a value of g of 32. 32. So I have g is equal to 32. So my initial goal was to write a function of this form that will give me the position of the object if I give it the time in seconds that it has been falling. So let's go ahead and do that. So I have the s of t, that's what I'm looking for. I'm looking for a position function in terms of time. So s of t, or position as a function of time, is the way you'd read that, is equal to negative 1/2 times g, which we just found to be 32, times t squared, plus v naught, which we found to be 48, times t, plus s naught, which we found to be 192. So here's my position function. The position of the object in terms of time in seconds is going to be negative 16 t squared plus 48 t, and then plus 192. Now, this answers a lot of questions for us. Like I said, the initial velocity of the object is 48 feet per second in the positive y direction, or up. The initial height that the thing was launched from was 192 feet above the ground. And if I feed this function a time, it'll tell me how high the object is from the ground. So for instance, if I said, how far is the object from the ground after 5 seconds, that would just be finding the s of 5. Or if I said, how far is the object from the ground after 6 seconds, that would just be finding the s of 6. Also, if I were to ask the question, when does the object hit the ground? Well, when the object hits the ground, its height above the ground is going to be 0. So what you'd be looking for are the t-intercepts, because the t-axis is the horizontal axis here. You'd be looking for the t-intercepts, which are kind of like the x-intercepts, for this parabola. So this is how we look at one physical application of the quadratic function, and this is called projectile motion.